Trigonometry, Chapter 6, Inverse Circular Functions and Trig Equations, Section 2, Solving Trig Equations, Video 2, Basic Linear Trig Equations, Part 2. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we described a technique for solving basic linear trig equations. We isolated the trig function, then used quadrants and reference angles to find the solutions within one period. We then determined the general solutions. In this video, we look at more examples of basic linear trig equations, including one with a not-so-nice angle. You'll see what I mean when we get there. For example, let's find the general solutions to square root of 3 tangent theta minus 1 equals 0. Think about how you would start. First, solve the equation in one period. Since the period of tangent is just pi, not 2 pi, we first solve over the interval 0 to pi. If we isolate tangent of theta, we get tangent of theta equals 1 over the square root of 3. Or if you rationalize the denominator, square root of 3 over 3. This should be fairly transparent. All we would have to do is add 1 to both sides. That would give us square root of 3 tangent theta. Let me use my stylus here. Maybe. Square root of 3 tangent theta equals 1. And then we would divide both sides by the square root of 3, which would give us tangent of theta equals 1 over the square root of 3, or if we rationalize the denominator, square root of 3 over 3. Now, since the constant is positive, we want a solution in quadrant 1 only. Now, if you think in quadrant 3, that's not within the first period of 0 to pi. And since tangent inverse of square root of 3 over 3 is pi over 6, and that's already in quadrant 1, this is our one period solution. To find the general solution, simply append a period multiplier to the specific solution. The period of tangent is just pi, so the general solutions to the square root of 3 times tangent of theta minus 1 equals 0. Our theta equals pi over 6, our specific solution, plus our period counter, pi n. N is an element of the integers. So the only difference between this one and the one in the previous video is our period was only 0 to pi. So we only had the one specific solution. And of course, the period multiplier is pi n, not 2 pi n. Now let's try one more. Find the general solutions to 5 cosine theta plus 3 is equal to 0. Again, I want you to think about how you would start this. To solve a basic linear trig equation, you start by isolating the trig function. Think about the 2 steps necessary to do that. They're pretty transparent. First, we'll find the solutions in one period, 0 to 2 pi. If we isolate cosine, we get cosine of theta equals negative 3/5. Subtract 3 from both sides, then divide both sides by 5. We look for quadrants where cosine is negative. That would be quadrants 2 and 3. Again, when you're looking for the quadrants, don't forget this. That was supposed to be a C down there. We want to know where cosine is negative, so let's cross out where it's positive. And that leaves us quadrants 2 and 3. Okay. Now, our reference angle is cosine inverse of 3/5. Remember, we do the inverse trig function of the absolute value of the constant because our reference angle is acute. It's between 0 and pi over 2. Now, 3/5, that is not the value of cosine for a nice angle. It's not 30, 60, 90, 45 degrees or anything like that. Thus, we approximate using a calculator. Using a calculator in radian mode, always use radians unless it says otherwise. We approximate the reference angle as cosine inverse of 3/5 is approximately 0.9273. So there's our that's our reference angle. In quadrant 2, a reference angle of 0.9273 when measured from standard position gives us theta is approximately pi minus 0.9273, which is approximately 2.214. And again, if you have trouble seeing that, then just draw a quick picture. We put the reference angle in quadrant 2. So we'll just say this angle goes here. But we want to measure it from over here. Altogether, it makes a semicircle. So it would be pi minus the 0.9273. So how do we do it in quadrant 3, the location of our other solution? Well, in quadrant 3, the same reference angle when measured from standard position would be pi plus 0.9273. Again, if we put that reference angle in quadrant, come on, quadrant 3, so if we put this angle here and then measure it from standard position, it's a semicircle pi plus that reference angle, which is about 4.0689. Since the solutions are in one period are 2.214 and 4.0689, then the general solutions are those things plus 2 pi n, where n is an element of the integers. So if your constant when you're doing the inverse trig function is not associated with a quadrant or a quadrantial angle or a special triangle, get ready to use your calculator to get an approximation. Now you try. Pause the video and try the following. Solve 5 plus secant theta equals 3. Give one period in general solutions. And solve 4 sine theta minus square root of 2 equals 0. Give one period in general solutions. Pause the video, give it a try. Here's your fair warning if you haven't paused the video yet. Solutions in 3, 2, and 1. For number 1, if you isolate it, you get secant of theta equals -2, which implies quadrants 2 and 3. The reference angle is secant inverse of 2, which is pi over 3. If you had trouble with that, then you could have done cosine inverse of 1/2 by converting secant theta equals -2 to cosine theta equals -1/2. But the reference angle is pi over 3. Double check that. Yes. Measure that from standard position in each quadrant to get 2 pi over 3 and 4 pi over 3. And then our general solutions are those plus the period multipliers. For the second one, if we isolate sine, we get sine of theta equals square root of 2 over 4. That's positive. So we want solutions in quadrants 1 and 2 where sine is positive. The reference angle is sine inverse is square root of 2 over 4, which is approximately 0.3614. If we measure those from standard position, in quadrant 1, that is the angle, and in quadrant 2, we would subtract it from pi. Then we would add the multipliers to get our general solutions.